Now, Gauss Law in electrostatic field. Here we have agenda of field line, introduction of electric field, Gauss Law, mathematical equation of electrostatic field, and application of Gauss Law. The introduction of the field line or flux. When actually it is introduced by the Michelson Friday, and what happened? Michelson feel that the strength of the electrostatic field near a body is described by the lines that come out from this body. Okay, and particularly what he predict or interpreted that the particular unit area from which how much lines comes out of that field is actually the flux. The line of forces, or they are the imaginary line, you can say, or curve drawn from one target place to another. That is, from it start from positive charge or end on the negative charges. They never cross each other. They never interface with each other, and they never tangent. They are tangent to the curve at any point and give the direction for the electric field at that point. Now, electric flux over the surface is defined as a number of the field line per unit area passing through a small surface normal to the area. That is what we known as a flux. Now, flux, what we said, the electric field, that is field lines passing through the area dA, integration over the surface E dot dA. Now, dA is nothing but the n cap dA, and E cap n cap they are in if same direction, that is the area we are taking and the electric field direction are parallel to each other, then EA cos of theta equal to 0. Theta equal to 0, we will get EA phi equal to EA. But if they are perpendicular to each other, that is area which we are considering under the consideration having a normal perpendicular to the electric field, that is 90 degree, then there is no flux. Now, field as electrostatic field, as we know, is nothing but Q r cap divided by 4 pi epsilon naught r square. Now, as I already discussed with you, that field line they started from positive charge, ends on negative charge. Okay, or they always have a direction. Electric field is tangent to the field line at any point, and field line diverge as the field get weaker. Now, what it diverge? Because of the 1 upon r square. As you move away from the body at the very large distance, due to this 1 upon r square factor, the strength of the field is get weaker and you will not find the field. Okay, and it converge at as the field gets stronger, or जैसे जैसे वो you come towards the body, it start converging, it start attracting to you. Okay. Now, Gauss Law statement. Surface integral of a normal component of electric field over a closed area is equal to 1 upon epsilon naught time the algebraic sum of the charges enclosed within the surface. Now, what we say, surface integral of a normal component over a closed surface, that is integration over a closed surface. Okay. Now, this is the integration of flux over a closed surface. Now, what we already discussed, the flux is nothing but electric field coming out per unit area, E dot dA. So, we will write in place of infinitesimally flux, smallest part we will take E dot ds. ds is the area, we can write in place of dA, ds. Here we have considered ds is the unit area. Okay, and when we take the integration, we come out with the solution, the algebraic sum of total charges divided by epsilon naught. How we approach to this conclusion, we will see below. Now, what we says, flux is nothing but integration over the surface E dot dA. Okay, by the divergence theorem, this is nothing but integration over the volume del dot E dV. dV is the volume. Now del dot V dV is nothing but Q by epsilon naught. If we write Q as an integration over the volume rho dV, we will substitute that in the place of this Q by epsilon naught, rho by epsilon naught, and since there is a volume integration at the both sides, we will cut it down. Then del dot E is nothing but the rho by epsilon naught. This is what we have a derivative form, and this is what we have a integration form, okay, of the Gauss law. Now, proof of the Gauss law. Okay. Now consider a point charge Q inside an arbitrary, any types of surface, arbitrary. It doesn't matter which type of surface you are choosing, but a point charge Q at the place of O, and take an arbitrary ds, segment of the surface. Okay. Now consider surface element ds with the unit vector n cap at the distance r from the point O or from the point charge Q. Now we will find the electrostatic field coming out of this surface area ds due to the charge Q given by E is equal to 1 for Q by 4 pi epsilon naught r square, as we know, and ds is nothing but n cap ds. Now when we multiply these two terms, what we will, flux coming out of this ds element is equal to d phi E is equal to E dot ds. Now E dot n cap ds, E is this term, r cap n cap is the unit vector, therefore r cap n cap is equal to r n cos of theta. Second, what we have already learned before, previous lecture, that d omega, solid angle, since you can say they are forming the solid angle over here. The solid angle d omega is nothing but ds cos of theta divided by the distance r square. Now, if we substitute this value into the equation of the d phi, what we will get, q r n cos of theta 4 pi epsilon naught r square is equal to q 4 pi epsilon naught r and n has value unit vector, since it has a magnitude 1 1, it will be come out cos of theta ds divided by r square is nothing but d omega. Now integrating over the entire surface S for finding the entire surface flux due to the entire surface. So integration over a closed surface d phi, we will take the integration of whole this. Now q by 4 pi epsilon naught is constant quantity. We will take only the integration of the solid angle d omega, which is nothing but, as we have learned in the previous lectures, nothing but the 4 pi, a constant quantity. This 4 pi get cancelled, remains q by epsilon naught. So what we conclude, that flux coming out of this surface is nothing but q by epsilon naught. And what we have, flux is nothing but integration over a closed surface E dot dA. So automatically what we conclude, that integration over a closed surface E dot dA is nothing but q by epsilon naught, integral form of the Gauss law. Second, let's suppose the charge Q is not inside the surface. We have considered the case, we have put the constraint that charge is inside the surface. Now let's suppose I remove that constraint and put the charge outside the surface. What will happen? When the charge is outside the surface, this point Q, there are two surface elements that will be, let it be, might affected. That surface elements are ds1 and ds2. Consider point charge Q outside the arbitrary surface at the point O. Consider the surface element S1 and S2. Both surface elements making the same solid angle with the point Q, so that we have working will be somewhat minimized in mathematics. And with the point unit vector n cap, this n cap of ds is coming out of this way and n2 cap above this way. Okay, at the distance, ds is at the distance r1 cap and ds2 at the distance r2 cap. from the charge q. Now net flux through the element ds1 and ds2 is given as d phi is equal to flux due to this plus flux due to this. Now flux d phi E1 d phi E2 is the electric field at point E1 ds1, electric field at this point E2 ds2. If we take n cap outside of the ds1 and ds2, we will get this equation. Now as we already discussed, n cap r cap is nothing but r cos of theta, and when we find that E1 cap and n1 cap, here what happened, we wanted to find the electric field in this direction above, okay, but n cap is in opposite direction below, okay, and at some angle theta. Let's say it is to be theta 1. Therefore this n cap is negative direction. We will get a minus of E1 cos of theta 1. When we substitute these two values, that minus of E1 cos of theta 1 ds1 plus of E2 cos of theta 2 ds2, okay, and we will put the value of electrostatic field, that is q divided by 4 pi epsilon naught r square, okay, r1 n1 cos of theta 1 ds1 and r2 n2 cos of theta 2 ds2. In this equation, what q by 4 pi epsilon naught is constant quantity, r1 n1 has a r unit vector, therefore having a magnitude of 1, it will finish 1.1 is nothing but 1. Cos of theta 1 ds1 divided by r1 square is nothing but the d omega solid angle at this point. The similar way, cos of theta 2 s2 ds2 divided by r2 is the solid angle by this cone. We will keep that. Since these solid angles are in a same line for the same cone, this will be cut it out having the same magnitude. So this will be cut it out, minus d omega plus d omega equal to 0, and we result into flux 0. Conclusion: if the charge is outside the body, then there is no flux in the surface coming out of the surface, okay. If the charge is outside the body, there is no flux coming out of the surface. If the charge is inside the body, there is a flux coming out of the surface. Now mathematical equation for the electrostatic field. Now divergence of an electric field. What we know from the Coulomb's law, the electric field due to the volume charge is equal to electric field 1 upon 4 pi epsilon naught q by r square. Now this q is changed with the integration rho beta. Rho is the charge density in the volume, beta, okay. Now take the divergence of both the side of the equation, that is del dot E over here also, del dot over here also. Now 1 upon 4 pi epsilon remains same, integration remains same, del dot r cap divided by r square rho beta. Now this del dot r cap divided by r square we have studied in previous lecture is nothing but 4 pi Dirac delta function r minus r prime. If we substitute that value, what we will get, it is nothing but 4 pi. Integration will come at r equal to r prime. Therefore, rho prime divide by 4 pi get cancel, epsilon naught. Okay. The curl of electric field. By again Coulomb's law, we know that Q is equal to Q r cap divided by 4 pi epsilon naught r square. We will take curl derivative at both the side of the equation, del cross E, del cross. Now q by 4 pi epsilon is a constant quantity, remains del cross r cap divided by r square, and this term del cross r cap divided by r square is to be calculated. Now taking the surface integration at both the side, when we take this in the consideration and apply the Stokes theorem, that is fundamental theorems of curve. Integration over a closed line r cap divided by r square dl. Now when we apply over here, what we find that integration over a closed surface del cross E dA is equal to q by 4 pi epsilon naught integration over a closed line r cap divided by r square dl. Now this integration result into the 1 upon r from, since starting point and ending points are same, it's a closed path integration. Therefore, starting point RA is equal to ending point RA, and that result that 1 upon R is 1 upon RA minus 1 upon RA. Both 1 upon RA है तो वो minus में 0 हो जाएगा, and we will result into 0. Application of Gauss law. Now, the surface area of a curved cylindrical surface will be 2 pi RL. 2 pi is the circumference of the, application of the Gauss law. Electric field due to the infinite wire. Okay. Now, in this problem, if we take an infinite wire having a charge positive, now consider a Gaussian surface over this infinite wire. The surface area of the Gaussian surface is having a circumference 2 pi r and having a length L. Okay. Now electric flux due to this particular Gaussian surface is coming out of the surface. That means surface area n cap and the electric field E both are parallel to each other. Now let's suppose phi of total phi is equal to integration over surface of this Gaussian surface E dot dA. Okay, and E dot dA is nothing but E integration of dA, and dA what we have said that circumference 2 pi r into the length L. Now according to the Gauss law, what we know, this phi is equal to nothing but the total charge Q, algebraic sum of charge Q divided by epsilon naught. Now algebraic sum of charge Q is nothing but rho divided by L. Rho into L. Now if we substitute rho into L in the place, okay, and on the left hand side we have E2 by RL, E2 by RL. This L and L get cancels. The electric field E is rho divided by 2 pi epsilon naught R in the direction perpendicular to the surface, that is n cap. Second problem, we will see the electric field due to the infinite plate sheet. Let's suppose we have an infinite plate sheet. Okay, and we will draw a Gaussian surface over here. This is a pin boxes. Okay, now this pin box A and this pin box, okay, one is directed from toward the left and another is directed toward the right. Okay, this is the n cap, this is the n cap. Now electric field E also directed toward the left and directed toward the right. That means there are three surfaces now. One is on the extreme left, one is on the extreme right, and one is the sheet, that charging sheet. Okay, so flux due to these three surfaces, that flux due to the S1 surface plus flux due to the S2 surface plus flux due to the S3 surface. Now this flux, S1 surface flux, is E dot dA cos of theta. Why? Because the area का normal और electric field का normal दोनों भी same हैं, parallel to each other है. Therefore EA cos of theta 0. Theta is nothing but 0 degree. Same way S2 के लिए भी this normal and the electric field they are parallel. Therefore, EA cos of 0 degree. But for this surface, n cap is at the 90 degree with the electric field. So EA cos of 90 degree. 90 degree is 0, nothing. Okay. Therefore, EA is choice of EA. Now we know by the Gauss law, total flux is equal to total charge divided by epsilon naught. Now here charge is sigma into A. Since we are talking about the surface, so we are taking sigma into A divided by epsilon naught. Therefore, when we cut it out A, we get E equal to rho by twice of the epsilon naught. Now, we have calculated for single plane sheet. If we kept both the two plane sheet parallel to each other, as the figure shows, okay, so what happened? If it is a positive sigma and if it is a negative, that means it has a positive charge, it has a negative charge. The positive charge will spread out and negative charge will contradict. So this is the positive charge direction. This sheet will spread out direction in this direction, in this direction, in this direction. Okay, and due to this negative charge sheet, the charges will come inside the sheet like this. As you can see, extreme left, these two directions are opposite to each other. That means they will cancel. Same way as to here, in the extreme right, these two directions again opposite to each other will cancel each other. But in between, you will find the direction is same. So here we will calculate the electric field. Now, due to single plate, what we have said, the electric field is sigma divided by 2 pi epsilon naught. Now we have two sheeted, the sigma divided by 2 pi epsilon naught plus sigma divided by 2 pi epsilon naught. Come out at 2 sigma divided by 2 pi epsilon naught, nothing but sigma divided by epsilon naught. Now, electrostatic field due to the charge conducting sphere. This is the charge conducting sphere. We will draw a Gaussian surface on that charge conducting sphere. Case 1. The flux over the Gaussian surface where Gaussian surface radius r is greater than capital R. Okay. Now flux is equal to integration over surface E dot dA. Integration over a closed surface we will take for this E dot cos of theta. See, theta is 0 here since the direction of E and dA is same. They are parallel to each other. Therefore, we will take theta equal to 0. Cos of 0 is nothing but 1. E will come out. Integration over a closed line dA. And this is nothing but the area of the sphere, which is nothing but 4 pi r square. Now 4 pi r square we will substitute over here. We will get E 4 pi r square is equal to flux. Now by the Gauss law, what we know that flux is equal to Q by epsilon naught. Now if we substitute this value, then electric field E is equal to Q 1 upon 4 pi epsilon naught r square r cap, for r is greater than or at least equal to at the surface of this capital R, at least equal to the surface of R. Now consider the Gaussian surface inside the sphere. Now from the Gauss law we know that flux is equal to E dA SQ by epsilon naught. Now when you look inside of this Gaussian surface, what you find, there is no charge inside enclosed within that surface, because charge's place lies only on the surface of the sphere. It does not lie inside within the Gaussian surface. Therefore Q equal to 0 and we will get this term as equal to 0. That means we conclude case 1, entire charge on the sphere was concentrated on the surface. The electrostatic field at any point inside the conductor of any shape is null vector. Okay. That means when small r is greater than or equal to capital R, we will get the electric field. But when small r is within the sphere, inside the sphere, the electric field is 0. Similar way, electrostatic field due to the charge conducting spherical shell. Now, case 1, flux over the Gaussian surface over the spherical shell. Now, phi is equal to integration over surface E dot dA. Again, okay, we will draw a Gaussian surface over the spherical shell, and we will try to find the flux, which is nothing but integration of surface E dot dA. Again, these are the perpendicular or parallel to the area vector. We will get cos of theta is cos of 0 degree, which is nothing but 1. E will come out, integration over a closed area dA, that is nothing but 4 pi r square, that is area of a sphere, and we will calculate. What you find, this is having similar result as the conducting sphere. That means the spherical shell will look like a sphere as before. Okay, there is no difference between this. Now consider inside the shell. Now again, inside the shell, when we draw Gaussian surface in this region less than capital R, there is no charge inside. Again, we will get nothing. There is null vector inside. That null vector electrostatic field inside the spherical shell.